Hello, today we're going to talk about de Moivre's theorem. De Moivre's theorem is easy to state. For any real theta and any integer n, then cos theta plus I sine theta to the power of n is equal to cos n theta plus I sine n theta. De Moivre never actually stated this theorem in his works. Some authors refer to de Moivre's theorem as only covering the cases for positive integer n. But we're going to assume that de Moivre's theorem is covering all integer n, and that's what we're going to prove. So we're going to prove this theorem in two ways. For proof number one, we'll start with the rule of exponents, namely a to the power of b, or to the power of c, is equal to a to the power of bc. Now if we set a equal to e, the base of natural logarithms, and b equal to I theta, and c equal to n, which is an integer, then what we get is that e to the I theta to the power of n is equal to e to the I n theta. But we know from Euler's formula that e to the I theta is cos theta plus I sine theta. And similarly, we know that e to the I n theta is cos n theta plus I sine n theta. Substituting those in, we get cos theta plus I sine theta to the power of n is equal to cos n theta plus I sine n theta. So the proof of de Moivre's theorem is very straightforward. But actually, this proof is something of a cheat, because de Moivre's theorem predates Euler's formula. That brings us on to proof number two, which is a more elementary proof. We're going to split the integers into three cases. Firstly, n equals 0, secondly, positive n, and thirdly, negative integer n. Now when n equals 0, the result's trivial. The left-hand side is cos theta plus I sine theta to the power of 0. Now given that cos theta plus I sine theta is not equal to 0, that then is equal to 1. For the right-hand side, cos n theta plus I sine n theta is equal to cos 0 plus I sine 0. Cos of 0 is 1, sine of 0 is 0, and so the result's equal to 1. So the left-hand side equals the right-hand side, and we've proved the case n equals 0. Now the proof for positive n we'll do by induction. For the base case, n equals 1, is trivial. Now suppose the statement is true for n equals k. In other words, cos theta plus I sine theta to the power of k is equal to cos k theta plus I sine k theta. If we now multiply both sides by cos theta plus I sine theta, what we get is cos theta plus I sine theta to the k multiplied by cos theta plus I sine theta equals cos k theta plus I sine k theta multiplied by cos theta plus I sine theta. Now on the left-hand side, that just combines to give cos theta plus I sine theta to the power of k plus 1. On the right-hand side, we expand the brackets and collect the real and the imaginary terms. For the real terms, we get cos k theta cos theta minus sine k theta sine theta. And for the imaginary terms, we get sine k theta cos theta plus cos k theta sine theta. But remembering the addition formulae for cosine and sine, that actually simplifies to cos of k plus 1 theta plus I sine k plus 1 theta. In other words, the result is true for n equals k plus 1. Well, we've shown that the result's true for n equals 1. We've shown that if it's true for n equals k, then it's true for n equals k plus 1. And therefore, the result is true for all positive n by induction. The next case that we need to consider is when n is a negative integer. If n is a negative integer, then minus n is a positive integer, to which we've already proven de Moivre's theorem applies. In other words, cos theta plus I sine theta to the power of minus n, which is a positive integer, is equal to the cos of minus n theta plus I sine minus n theta. But we know that the cos of minus x is equal to the cos of x, and the sine of minus x is equal to minus sine x. And therefore, 1 over cos theta plus I sine theta to the n is equal to cos n theta minus I sine n theta. Taking the reciprocal, we get cos theta plus I sine theta all to the power of n is equal to 1 over cos n theta minus I sine theta. What we need to do is to make the denominator of the right-hand side real. And we do that by multiplying top and bottom by cos n theta plus I sine n theta. If we do that, of course the numerator becomes cos n theta plus I sine n theta. The denominator becomes cos squared n theta plus sine squared n theta. And that's just an identity. That's equal to 1. And therefore we arrive at the result cos theta plus I sine theta to the power of n is equal to cos n theta plus I sine n theta. In other words, the theorem is true for negative n as well. Combining those three cases, we've proven de Moivre's theorem for all integer n. So what are the uses of de Moivre's theorem? Well, there are really three. Firstly, it allows you to express powers of sine and cosine in terms of multiple angles, like sine 2 theta or cos 3 theta. Secondly, it allows you to express multiple angles, such as cos 3 theta, in terms of powers of sine theta and cosine theta. And finally, it allows you to evaluate integer powers of complex numbers. What we're going to do now is look at a few examples which illustrate each of these uses. So we're going to start with a relatively straightforward example. Prove that sine 3x is equal to 3 sine x minus 4 sine cubed x. Well, using de Moivre's theorem, we know that cos 3x plus I sine 3x is equal to cos x plus I sine x to the power of 3. What we now do is to expand the right-hand side. That gives us cos x cubed plus 3 cos x squared times I sine x plus 3 times cos x times the square of I sine x plus the cube of I sine x. Now we've got an equality here. That means that both the real and the imaginary parts are equal. What we want are the imaginary parts. So, equating the imaginary parts, we can ignore on the left-hand side cos 3x and on the right-hand side any terms which are real. So what that gives us is that sine 3x is equal to 3 cos x squared times sine x minus sine cubed x. If we replace cos x by 1 minus sine squared x in the right-hand side, that gives us 3 into 1 minus sine squared x times sine x minus sine cubed x. Expand the brackets and combine terms and you get the required result, namely that sine 3x is 3 sine x minus 4 sine cubed x. The second question is rather similar to the first. Express cos 5 theta as powers of cos theta. Again, from de Moivre's theorem, cos 5 theta plus I sine 5 theta is equal to cos theta plus I sine theta to the power of 5. And again we expand the right-hand side. This time we need to equate real parts. If we do that, then what we get is cos 5 theta is equal to cos to the 5 theta minus 10 cos cubed theta sine squared theta plus 5 cos theta sine to the 4 theta. Now in fact the question asked us to express cos 5 theta purely in terms of cos theta. So what we need to do is to replace any occurrence of sine squared theta by 1 minus cos squared theta and sine to the 4 theta by 1 minus cos squared theta all squared. If we do that and then expand brackets, collect terms, what we arrive at is that cos 5 theta is equal to 16 cos to the 5 theta minus 20 cos cubed theta plus 5 cos theta. The next example is slightly different. Here we're required to express sine to the 5 theta in terms of sines of multiples of theta. We're going to start slightly indirectly we let z equal cos theta plus I sine theta. By de Moivre's theorem, z to the n is cos n theta plus I sine n theta, and z to the minus n is cos n theta minus I sine n theta. And here we've used the result that the sine of minus n theta is minus the sine of n theta. Well, if we take the second result away from the first, what we get is that 2I sine n theta is equal to z to the n minus z to the minus n. In particular, this means that 2I sine theta is equal to z minus 1 over z. Now the question asked us about sine to the 5 theta. So we take this equation and raise both sides to the power of 5. On the left-hand side, we have 2I to the power of 5 times sine to the 5 theta is equal to z minus 1 over z to the power of 5. And we can expand that. And we then collect terms involving z to the 5 and z to the minus 5 and so on together. Well, of course, z to the 5 minus z to the minus 5 is 2I sine 5 theta. Similarly, z cubed minus z to the minus 3 is 2I sine 3 theta, and so on. Consequently, we can simplify the above equation to 32I sine to the 5 theta is equal to 2I sine 5 theta minus 10I sine 3 theta plus 20I sine theta. All we need to do now is divide both sides by 32I, and we end up with the result sine to the 5 theta is 1/16 of sine 5 theta minus 5 sine 3 theta plus 10 sine theta. For our final example, we're going to look at simplifying a complex number raised to an integer power. In this case, we're looking at 1 plus I to the power of 6. Now we can write 1 plus I as being equal to root 2 into cos pi by 4 plus I sine pi by 4. Once we've got that, if we raise both sides to the power of 6, we can apply de Moivre's theorem to the bracketed term, and consequently the result is minus 8I.